Monte Carlo simulations in Python, from basics to projects. Welcome! In this lesson, we will explore Monte Carlo simulations with practical Python examples. You will learn probability basics, run hands-on simulations, analyze results, and complete a mini-project. Let us get started. Running the cell now. We need some libraries for working with numbers, data, and making charts. We import everything we need to run probability simulations, work with data, and create charts. Warnings are hidden to keep things tidy. NumPy lets us do math and random simulations. Pandas helps with data tables. Matplotlib and Seaborn make our graphs look good. Running the cell now. Try changing the list of imports and see what happens. What is a Monte Carlo simulation? A Monte Carlo simulation uses random numbers to model experiments. It helps you estimate answers by running many possible scenarios. Real-world example, you can estimate how likely it is to win a game or predict sales. Running the cell now. Let us try a simple experience, flipping a coin several times. We are simulating 10 coin flips, using H for heads and T for tails. The computer runs random flips and shows the results. You will see an array that lists the outcome of each flip. Running the cell now. Try increasing the number of flips. Now let us repeat the coin flip many times to see how close we get to the real probability. We flip a coin 10,000 times and count how often we get heads. We divide the heads count by total flips to get the estimated probability. This lets us check if flipping a lot gives us a value close to 1/2. Probability is a measure of how likely an outcome is. The result should be about 0.5 or 1/2, just like in real life. Running the cell now. Remember, more simulations give us a better estimate. Descriptive statistics, average and spread. Descriptive statistics help summarize our results. The mean measures the average. The standard deviation tells us how spread out the data is. Let us calculate these values for our simulations. Running the cell now. Let us roll a standard die 1,000 times and see what the average and spread look like. We simulate rolling a 6-sided die 1,000 times and save each result. We calculate the average, mean, or of all rolls. We also find the standard deviation, showing how much the numbers vary. This helps us understand how random events behave over time. The result should be close to what we expect for a fair die. Running the cell now. Can you explain why the average stays close to 3.5? Sometimes, real data is missing values. We should learn how to deal with this. We copy our die rolls and make some values missing using an ANFA, not a number. Missing data can happen in real experiments. We calculate the mean using a function that ignores missing values. It helps you work with real data that is not perfect. Running the cell now. Try different ways of handling missing values and see what changes. Discrete distributions, the binomial. A binomial distribution models the number of successes in repeated yes or no experiments. Example, how many times do you get heads if you flip a coin 10 times? Let us simulate and plot it. Running the cell now. Now let us see what the results look like with a histogram. We simulate 1,000 experiments of flipping a coin 10 times each. Each result counts how many heads appeared out of 10. We plot a histogram, which shows the probability for each possible number of heads. The x-axis shows how many heads happened in an experiment. The y-axis shows how often each number comes up. The chart helps you see the most likely outcomes. Now you are seeing probability in action as a graph. Running the cell now. Try changing the number of trials and see how the shape changes. Continuous distributions, the normal curve. Many natural outcomes follow a bell-shaped curve called the normal distribution. Examples: heights, test scores, errors in measurement. Let us create and visualize a normal distribution. Running the cell now. Let us simulate data where outcomes are centered on 0 and spread out evenly on both sides. We generate 10,000 data points from a normal distribution, centered at 0. KDE means kernel density estimate, which draws a smooth curve on the histogram. The bell-shaped curve appears because most values are near the mean. Wider or narrower shapes happen if you change the spread. This mirrors many things found in nature. We plot the data to see the famous bell shape. Running the cell now. Try shifting the mean or changing the spread and watch what happens. Monte Carlo lets us see important ideas, like the central limit theorem. First, we make a large population with values spread out evenly from 0 to 10. From that, we take many random samples, each of size 50, and find their averages. We plot those averages in a histogram. Even though the original data is not a bell curve, the sample means look normal. This demonstration gives you a powerful tool. Averages from random samples become bell-shaped, no matter the source. This is called the central limit theorem. Running the cell now. Try using smaller or larger samples and see the effect. Let us use real data now. We will estimate a range where the average tip is likely to be. We load a real data set about tips from a restaurant. We take a small sample of tip amounts. We find the average and how much the values vary. A confidence interval is a range we are pretty sure contains the true mean, based on our sample. We use a special t-distribution to get the correct margin of error. The code prints the lower and upper limits, where we can expect the real average to fall most of the time. Running the cell now. Change the sample size to see how the confidence interval becomes tighter or wider. Let us try a hypothesis test. Do people tip more at dinner than at lunch? We split the real data into dinner tips and lunch tips. We use a t-test. This checks if two things really differ, or if it is just chance. The p-value is how likely it is to see this difference by chance. If p is less than 0.05, we say there is good evidence that tips are different. The code prints the test result clearly for you. Running the cell now. Switch which group you compare to explore different questions. Now let us check if bigger bills usually mean bigger tips. We measure two quantities, correlation and covariance. Correlation measures how two things move together on a scale from -1 to 1. Covariance shows the direction of a relationship but not how strong it is in general. Here, a positive correlation means bigger bills usually come with bigger tips. These numbers help you see connections between different things. Running the cell now. Find two new columns in the data to compare their correlation. Let us make a prediction. Can we estimate the tip amount from the size of the bill? We use linear regression, a way to draw the best fit line through the data. First, we pick total bill as input and tip as the outcome. We add a constant term to our features to match the math. The OLS model finds the best coefficients to fit the line. We print out the summary. Look for the coefficient on total bill that suggests how each extra dollar affects the tip. This helps you make simple predictions. Running the cell now. What does the intercept mean in this result? Let us go further. We will predict who survived on the Titanic using logistic regression. We load the Titanic dataset with information about passengers. We keep a few columns and fill in missing values for simplicity. Survival is what we want to predict. It is either 0 or 1. We split data into training and test sets to check predictions fairly. We use a logistic regression model. This works for yes or no outcomes. We train the model using passengers we already know about. We test how well it predicts survival for new data. The printed accuracy tells how often the model gets it right. This is a key real-world use of simulation in Python. Running the cell now. Try predicting with more columns or a different random underscore state. Some data changes over time. Let us see a real historical example with airline passengers. We load airline passenger data from a public website. We treat the dates as real date values using pandas. We plot the number of passengers for each month. Time series data helps us notice trends, such as growth or seasonal ups and downs. This type of analysis is common for bookings, weather, and more. Look for patterns repeating over months and years. Running the cell now. What do you notice about the growth over time? Bayesian thinking lets you update what you believe as new results come in. Imagine flipping a coin 20 times and getting 13 heads. We are not sure if the coin is fair. Bayesian statistics lets us update our guess based on the results. The beta distribution represents our belief about how likely heads is. As we see more data, this curve gets sharper or shifts right or left. The plot shows which probabilities are most likely after seeing the outcomes. This is a key idea behind Bayesian Monte Carlo simulations. Running the cell now. Try adjusting the number of successes to see what changes. Let us try a mini project. Imagine a dice game where you win if you get 15 or higher with 3 dice. We set up a game, roll 3 6-sided dice. If the sum is 15 or more, that is a win. We use a function to play the game over and over. After 10,000 games, we count the wins to estimate the probability. This lets us see how likely you are to win without doing the math by hand. Monte Carlo is perfect for testing game strategies. Running the cell now. Can you tweak the win condition? See how it changes your chances. Now for our second mini project. Use Monte Carlo to understand variation in daily COVID-19 cases. We get daily COVID-19 case numbers for the United States from an open dataset. We convert the wide format to long format using MELT. We take 2-week samples and find their average new cases per day. We repeat this process 1,000 times. The histogram shows how the daily average might look over different random periods. This method helps track uncertainty in pandemic numbers. You can use similar tools for any time series data. Running the cell now. What do you notice about the spread of averages? Here is a YouTube tip. Subscribe and comment if these simulations helped you. Best practices and troubleshooting. Use enough simulations for stable results. Start with 1,000 repetitions or more. Make sure to handle missing or weird data before analysis. Keep random seeds for reproducibility. Visualize your simulations to catch errors early. If you get confusing results, check your code and try different settings. Running the cell now. Extra tips. Use vectorized operations in NumPy for speed. The more random samples, the more accurate your estimates if it runs quickly. Save seeds or states if you want to repeat or share exact results. Try to explain your findings in plain language to others. Running the cell now. Practice challenge. Make your own simulation. What is the chance to draw at least one ace in 5 cards from a deck? Use Monte Carlo to estimate the probability of rolling doubles at least twice in 5 rolls of 2 dice. Try picking your own real dataset and find a creative scenario to simulate. Share your solution in the comments. Running the cell now. Recap. What did you learn? You learned how to build basic simulations with Python, analyze randomness and uncertainty, handle common data problems, visualize distributions, apply simulations to real-world datasets. Practice is the best way to master Monte Carlo. Experiment, ask questions, and have fun. Running the cell now. Thanks for learning Monte Carlo simulations. If you enjoyed this lesson, please subscribe and like for more Python and stats tutorials. Comment your results or share improvement ideas below. Happy simulating! Running the cell now.